Hello everyone. Thank you for attending today's session. Today we have Dr. Selim Gunay from PEER. He's a research scientist here, and he'll be talking about nonlinear dynamic analysis perspectives from element removal and hybrid simulation. So thank you, Dr. Gunay, for presenting, and it's all yours.
Okay, thank you, Pawan, for introducing me and also for inviting me to the for this presentation in the OpenSees group. I actually prepared two sets of slides, one for the hybrid simulation and the other one for element removal. So I will start with hybrid simulation. This is the title of my presentation for the hybrid simulation. And I mentioned, lessons for hybrid simulation, but basically lessons here in the lack of a better word. So I here mostly mean some experiences that we, obtained over the years that basically we can potentially use towards increasing the efficiency of nonlinear dynamic analysis and maybe reducing the convergence issues. So then to start with, basically hybrid simulation, as the name indicates, is this method that kind of innovatively combines numerical or analytical simulation with experimental simulation. So this method actually started in 1970s, initiated by Professor Main at Berkeley and Professor Takanashi at Japan, probably independently. And there have been a lot of developments over, the last 50 years or so, and there has been a lot of uses. So then to explain the method here, basically we see, the structure that consists of beams, columns, and the shear wall. So basically, if we have all the information that we need to be able to model all these components properly and accurately, all the way from elastic response to collapse, then this numerical model is basically sufficient to explore the dynamic response of this structure. But let's consider an hypothetical case where, let's say, these two columns have been retrofitted with a new, let's say, retrofit technique or new materials that we don't have any experimental data. So in that case, we would not know how to model these two columns properly because we don't have data about them. And in such a case, if these two columns have reasonable contributions to the global response of the structure, then this numerical model will not be sufficient and the results from the simulation basically will not be correct. So in that type of a situation, hybrid simulation kind of helps us basically by removing these two elements from our numerical model and replacing them by their, let's say, their counterparts in the lab. So then what we are doing is we are still simulating the response of the structure, but these two elements are not numerically modeled, but they are basically represented in the numerical model by testing them. So, and during the hybrid simulation, and we call these experimental substructures and the rest of it numerical or analytical substructure. And during the simulation, these two substructures basically interact with each other. So then what we are doing is actually we are computing the, let's say, the dynamic response of the structure. So in that regard, it is not any different than nonlinear dynamic simulation or nonlinear dynamic analysis. We are basically using the same methods and solutions. So we still need an equation of motion or equations of motion, and we still need to solve these equations of motion using numerical integration methods. But the only difference at this point from regular nonlinear dynamic analysis is in order to be able to proceed with integration time steps, we need to communicate with the lab. So that's the main difference. So then here we have a simple 2 degree of freedom example, and we have two springs, and the top spring is basically this analytical substructure that is modeled in the computer, and the bottom spring is basically this specimen in the lab, and we have basically these two masses and Rayleigh damping for this model. So we can call this basically a hybrid structure. So then here, as I mentioned, we basically need to first formulate the equations of motion for this. And here, this is our equation of motion. And we need to basically solve this using numerical integration. And here, if we look at the restoring force vector, if we consider the restoring force of the analytical component, analytical spring, basically it is computed, right? And but the restoring force of the specimen, which is denoted with this F sub E, basically it is measured directly from the lab. So then now we can basically see how the numerical integration, how we would apply the numerical integration on the equation of motion of this 2 degree of freedom system, which is basically a hybrid structure. And I'm sure most people are familiar with this, but just to elaborate one more detail before starting the integration method, basically once we set up or formulate the equation of motion like this, we do a discretization in space such that we basically set our degrees of freedom U1 and U2. So then when we are basically solving this using numerical integration, we are doing another set of discretization, which is the discretization in time. So then in that case, basically we are having integration time steps, and we are basically solving for the unknown quantities for each discretized integration time step. And here, basically, we know the mass matrix, the damping matrix, and this excitation force vector on the right-hand side. And we are basically using these numerical integration methods to solve for the unknown quantities of accelerations, velocities, displacements, and the corresponding restoring forces. So, and I generally find this explicit Newmark integration, or I generally find it more suitable to use the explicit Newmark integration method to explain this process, because it doesn't have iterations, so it is basically a 4-step straightforward procedure. So if we look at the steps of this, as I mentioned, we have these discretized time steps, and here I plus 1 indicates the next time step, and I indicates the current time step. So then in the first step of the integration, one integration time step, basically we compute the displacement at the next time step using the quantities from the previous one, using this Taylor expansion or finite difference equation. And the next step is basically to compute the restoring force vector. So then basically we have two sets of elements here, right? So for the one that is analytical, for this force F sub A, we basically compute in the regular way that we are doing in nonlinear dynamic simulation. We basically obtain the corresponding force from the force displacement, defined force displacement relation of this spring, using constitutive relations. So here, until now, nothing is different from nonlinear dynamic simulation. So now the difference is basically at this step. So here, basically to compute this F sub E, we basically need to impose or apply this computed displacement U1 to the test specimen, and then measure this again from the lab. So then now, after doing this, basically we have our restoring force vector completed. So then, as I mentioned, this is the difference of hybrid simulation from regular nonlinear dynamic analysis. And the following two steps are also the same as in nonlinear dynamic analysis. So in the next step, we basically compute the accelerations by solving this linear system of equations, and then compute the remaining quantity, the velocities, using another difference equation. And then basically this completes one time step, then we move on to the next one after this. So then what is the role of OpenSees in this hybrid simulation process? So basically, to be able to address this question, we can go over the list of components or platforms that we would need to conduct hybrid simulation. So what are those components? The first one is obviously we need a computational platform basically to conduct this numerical integration, let's say the explicit numerical integration. And also we need this computational platform basically to compute the restoring force for the analytical substructure, as we have seen in the previous slide. And I didn't show the tangent stiffness matrix there because explicit Newmark doesn't need that. But if you are using some other integration methods, some of them requires tangent stiffness matrix. So we also need the computational platform for that purpose. So this is the first component. And the second component is basically this transfer system that consists of controllers and actuators, such that we can apply the computed displacements to the specimen in the lab and measure the corresponding forces again from the specimen. And so these are the two components, and obviously we need a third component, which is the interface between the computational platform and the transfer system. So then if we go back to the first one, as a computational platform candidate, OpenSees is actually a great candidate to be used in hybrid simulation. I'm saying this not because now I'm presenting in the OpenSees support group, but actually it is because of these reasons. And particularly because of OpenSees being a hybrid simulation compatible platform. And why is this important? This is important because as I will show in the coming slides, we basically cannot use any integration method in hybrid simulation. So we need hybrid simulation compatible and mostly explicit integration methods in hybrid simulation. And these are not that well known as compared to other regular integration methods. And the documentation is a bit less compared to others, but actually OpenSees includes these types of hybrid simulation compatible integration methods. And let's consider a case that we want to use another method. And since the platform is open source, we can basically implement that new integration method. So that is the advantage. And just to mention about the interface, basically, we used OpenFresco together with OpenSees in hybrid simulation. And OpenFresco is quite similar to OpenSees in the sense that it's also object-oriented, and it is an open source platform, again, developed by Professor Main and Andreas Schellenberg from also UC Berkeley. And so, as I mentioned in my opening slide, basically we use OpenSees in hybrid simulation centered on the idea of considering the specimen as a part of our numerical model. So in that regard, how do we introduce the specimen to the numerical model, right? So we still need some commands to do that. And for that, we use this experimental element command. And this is just an example for the two-node link experimental element, which also there is a regular version of the two-node link element. And here, basically the description of this element, we do it in the same way as we do in a regular numerical model. We have the tag of the element, start node, end node, and so on. But here, the main difference is we use this cite command such that this allows us to be able to make these communications with the lab in terms of sending the forces and obtaining back the, sending the displacements and obtaining back the forces.